Welcome back. In this video, we are going to solve example 7.1 that is taken from chapter number 7, Transverse, Shear, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is the beam shown in figure 7-A is made from two boards. Determine the maximum shear stress in glue necessary to hold the board together along the seam where they are joined. So you can see this is the beam, and here there is a roller support, and at this end we have pin support, and this beam is acted upon by a uniformly distributed load of 6.5 kilonewton per meter over a length of 4 meter. And this beam is made of two boards that are glued together, and the glue is at this point. So you have to determine the maximum shear force in the glue necessary to hold the board together. So let's start with the solution. The first step is that if I remove this roller support at this point, so we will have a reaction force. Let this reaction force is R1, and if you remove this pin support at this point, so you will having reaction force R2. Let this is your point 2 and this is your point 1. So first we will find this R1 and R2 by using equation of equilibrium. So what are these equation of equilibrium? The first equation of equilibrium is that sum of all moments that is acting about point 1 is equal to 0 and taking the counterclockwise moment as positive. So you can see there is a 6.5 kilonewton per meter load, and this load when converted into a point load, so I can say this load will be 6.5 multiplied by 4, clear, and that will be equal to 26 kilonewton. Okay, now this load will act at a distance of 2 meter from either this side or from this side, so whichever you want. So I can write it 2 meter, and this will be also 2 meter. So by applying this equation of equilibrium, we can say that this load, which is 26 kilonewton, and the perpendicular distance is now 6 meter, and this is producing clockwise movement, so it will be negative. So I can write it minus 26 multiplied by 6. The second moment about point 1 is this load R2, and perpendicular distance is 8 meter, and this is producing counterclockwise, so it will be positive. So I will write R2 multiplied by 8 is equal to 0. So from here we will get 8 times R2 is equal to 26 multiplied by 6, and this R2 will become equal to 26 multiplied by 6 divided by 8, and when you solve this you will get this R2 will become equal to 19.5 kilonewton. Now we will find this second term, that is R1, by using another equation of equilibrium, that sum of all forces along y direction must be equal to 0. Upward force is taken as positive. So you can see R1 is upward, so plus R1 minus 26 plus R2 is equal to 0. So R1 minus 26 plus 19.5 is kilonewton is equal to 0, and from here we will get R1 will be equal to this. R1 will be equal to 6.5 kilonewton. Now we have this R1 and R2. So what we are going to do is that we will draw the shear force diagram in order to find the maximum shear force, because we know that maximum shearing stress is equal to maximum shear force into Q max divided by I into T. So we will find this maximum shear stress by using the bending moment shear force diagram. For this I am drawing to this beam, the free bar diagram of this beam. Here we have R1, which is 6.5 kilonewton, and here we have R2, which is 19.5 kilonewton. And there is a distributed load acting over a length of 4 meters. So let this is that distributed load. This length is 4 meter and this length is also 4 meter, and the distributed load was 6.5 kilonewton per meter. 6.5 kilonewton per meter. And when we will use two line from the end of this beam. So I will draw two line from the end of beam, and there is a horizontal line to show the length in meter. So this is x in meter, and there we have a shear force in kilonewton. Okay, starting from the very first point, we have R1, which is 6.5. So let me zoom it. Let this division is 5 kilonewton. This is 10. This is 15 kilonewton. So here minus 5, minus 10, minus 15, and minus 20. So I will choose first point. At first point we have R1, and R1 is 6.5. So let 6.5 lies over here. So you can see that moving from point 1 till the point of distributed load, there is no other load, so it will remain horizontal till this point. So I can draw a line like this till this point. Now you can see you have a distributed load over here. So this distributed load, when multiplied with this load, will give you minus 26. So here you have 6.5, and at this end you have minus 26, and that will go to minus 19.5. So at the end you have minus 19.5, which will be this point, minus 19.5. Now you can see that this distributed load is a horizontal line with 0 degree, and it is downward negative. So shear force will be a 1 degree line, and its slope will be decreasing. So we can just join these 2 points in order to get this line. And at the end you can see you have plus 19.5. So minus 19.5 plus 19.5 will bring this to 0. So this will be your shear force diagram. Okay, so from this shear force diagram I can write it here. From shear force diagram we see that maximum shear stress absolute value is 19.5 kilonewton. Now you can see that we have find out this Vmax. So we will find this I for this section, which is T section, that is made from the wood. So it is necessary to determine the neutral axis for this beam. So for neutral axis, I can first find the centroid or neutral axis of this beam, and this neutral axis lies, for this neutral axis I have formula that y dash is equal to sum of y dash bar into A divided by sum of area. So what I can do is that you can see this is the cross section of the beam. So here I can say we have two things. One is this one, two boards. One is this one, and second one is this one. I can write it as number 1. Let this is your first one and this is your second one, and we will take this horizontal line or the base as reference. So from reference line, this formula will become equal to y1 bar into a1 plus y2 bar into a2 divided by sum of area a1 plus a2. Now we can see that what is a1. So a1 is equal to this length, width and height is 150. So a1 in meter is 0.03 multiplied by height is 0.150. And what is y1 dash? So y1 dash is distance from this reference line till the mid of this. So let the mid of this is this one. This is y1 dash, and this y1 dash will be equal to 150 divided by 2. This is 150, so 150 divided by 2 is 75 millimeter. So 75 millimeter in meter is 0.075 meter. What is A2? So A2 is this area, you can see. So its area is 150 by 30. So I can write it 150 in meter is 0.150 and 30 is 0.03. And what is Y2 dash? So you can see Y2 dash is distance from this reference line till the mid of this section. This is your Y2. This is reference line. Okay. This is Y2 dash. Okay. And this Y2 dash is 30 divided by 2. This distance is 15. So I can say total height is 180. So 180 minus 15 is 165. So this Y2 is 165 millimeter. And in meter it is 0.165 meter. Now you have A1, Y1 dash, A2, Y2 dash. Just plug it in this formula. So let me plug it. So you will get Y dash bar is equal to Y1, which is 0.075 multiplied by area A1 is 0.03 multiplied by 0.150 plus Y2 dash. Y2 dash is 0.165 multiplied by area is 0.150 multiplied by 0.03 divided by sum of all the areas. So area A1, you can see area A1 and A2 both are same. So I can just write it. I do not have space over here. So I can just simply write it 0.03 multiplied by 0.150. So when you solve this, you will get location of centroidal axis or neutral axis, and that comes out to be 0.012 meter. Or you can say this Y dash is equal to 20, 0.12. Okay, make a correction when you calculate it. This Y dash is 0.120 meter. Or in millimeter, it is 120 millimeter. So as I am using meter, so I will use this value. But let me show you that neutral axis from the base will lie. This will be the neutral axis, and this distance will be equal to Y dash. This Y dash is equal to 120 millimeter. Now what we will do is that we will find moment of inertia I. So for I we have formula by using parallel axis theorem. So for first element, this one, we have 1 over 12 B1 H1 cube plus area A1 into D1 square plus moment of inertia of the second, which is 1 over 2 B2 H2 cube plus area into D2 square. Clear? So how we'll find this? So let's put the value 1 over 12. What is the height of this, base of this? So base is 0.03 meter and height is 0.150 meter. These values are in millimeters, so we will convert this. I can write 1 over 12, base is 0.03 and height is 0.150 cube plus area. Area is this base, which is 0.03 and height is 0.150. And what is D1? So D1 is distance from neutral axis till the mid of this section. So you can see this distance is 120 and this distance is 75. So you can get 0.120 minus 0.075 will give you D1. So I will write it over here. This distance will be D1. So D1 is 0.120 minus 0.075. Okay. Whole square. This will be the moment of inertia of the first plus 1 over 12. Now you can see that base is, for this is section 2. So base is 0.150 and height will be 0.03. So I can write 0.150 multiply by 0.03 whole cube plus area will be 0.150 multiplied by 0.03. And what is d2 square? So let me show over here. D2 is distance from neutral axis till the mid of this section. This is d2. So I can first show you this is d2, and d2 can be obtained if you take this total height, which is 180 millimeter, and then you subtract this 120, and then half of this, which is 15 minus 15, will give you this d2. Clear? So I can write d2 is 0.180 minus okay, d2 is, let me check it again. d2 is distance from neutral axis till the mid of this section, and you can see from the mid of this section this is y2. So simply we can say 165 minus this distance 120 will give you d2. So I will write it 0.165 minus 0.120 whole square. Okay, when you solve this you will get the moment of inertia I for this T section wooden beam, and this will be equal to 27 into 10 raised to power minus 6 meter power 4. Now you have the moment of inertia of this beam. Clear? And we will find Q max. So Q max can be obtained. We know the formula that Q max will be equal to y dash bar into area, and Q max for this, as we are finding out the maximum shear force for the glue that is in between this 1 and 2. So what we will find the Q max for this region. Okay, so what we will do is that this will be your area where you are finding the Q max at this region. So this will be the area A dash. So I can write this will be area is A, sorry, A, not A dash, A, and this area is 0.150 multiplied by the thickness, which is 0.03. And what will be y dash? So y dash is distance from neutral axis till the mid of this section, and that is d2, and that is 165 minus 120. Clear? Okay, so we can write this that Q max is y dash is 0.165 minus 0.120 into A dash is 0.150 multiplied by 0.03. Now when you solve this Q max by using your calculator, so you will get Q max will be equal to 0.2025 into 10 raised to power minus 3 meter power cubic meter. Clear? And again you can see you have now this value Q max, and what is T? So T is the thickness that will be counted in this portion, because this is the point of joining of these two with one by using glue. So we will take thickness T is 30 millimeter. So I will write it here. T is equal to 30 millimeter, R in meter, it is 0.030 meter. Now you have all the values. What you can do is that you can just plug it, as we are finding maximum shear stress, which is equal to V max into Q max divided by I into T. So V max is this one. You can see that where I have written V max is this one, which is 19.5 kilonewton. So I can write 19.5 into 10 raised to power 3 Newton. What is Q max? So Q max is this one, which is 0.2025 into 10 raised to power minus 3. divided by I, and I, the value of I is there, which is 27 into 10 to the power minus 6, and thickness is 0.030 meter. So when you solve this, you will get 4.88 megapascal. Now what I can write is that maximum shearing stress at the junction of first board and second board where they have been glued is 4.88 megapascal. Okay, so if I draw the representation of this stress for this beam, so let me draw it over here. Let this is the board, the first board. So the shear stress will be like this. This will be the shear force that will acting like this. Why upward? Because you can see the maximum shear force is 19.5, and that will be at the end because this will be plus 19.5. So shear force is upward. So if I represent the shear force on this element is like vertical, so this will be V, and the representation of stress will be like this. So this shear stress will be 4.88 megapascal, and that will be tau. Now if I represent it on three-dimensional element, so this representation will be exactly like this, that these shear force are upward. So in order to balance it, there will be a longitudinal shear stress there. So this will be the representation, and I will represent it is the glue resistance to the, this is the glue resistance to the longitudinal shear stress that holds the board from slipping at the right hand support. So this was all about this example 7.1. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.